So, in the last lecture we have seen the definition of vector spaces, some of the example of vector spaces. In this lecture we will learn about vector subspaces, some of their examples and properties. Again our field will be the field of real numbers, that is R. So, we start with the definition of subspaces. So, if Rn is a vector space over R, so here we are saying vector space Rn, but in general it can be any vector space V. Then a subset of Rn is said to be a subspace of vector space Rn if S is also a vector space over the same field R. Means the set of vectors of S also satisfy all those 6 properties which we have given in the definition of vector space. As I told you, here I am writing Rn due to machine learning application, because in machine learning we will see usually the vector space Rn where n may be any integers. However, the definition holds for any vector space V over the field F. The alternate definition of this can be given as, if Rn is a vector space, then a subset S of Rn is said to be a subspace of Rn over the field R if the 0 vector belongs to S. So, whatever 0 vector we are having for V or Rn, that is also part of S. S is closed under vector addition, that is if x y are 2 vectors from S, then their addition x plus y is also a vector in S, and S is closed under scalar multiplication. Means if you take a vector x from S and a scalar alpha from the field R, then alpha time x which should be again a vector of S. So, this is the definition of subspaces. We are having a very important result about subspaces, that is which is coming from the alternate definition only, that let W be a subset of Rn, then W is a subspace of Rn over the same field if and only if the following conditions hold. The first condition is W is non-empty, and from where we are looking it, that there should be 0 vector in W. So, if there will be 0 vector, it will not be empty. Then if you take any 2 scalars, A B belongs to R and 2 vectors u v from W, then A times u from the previous definition, A times u is again a vector of W if W is a subspace. B times V is again a vector of W because W is a subspace, then A u plus B v is also a vector of W. So, this particular theorem is just coming from the definition which we have seen in earlier slide, that is the alternate definition. We can see from these 3 properties we can show all 6 properties of a vector space. So, these 3 properties implies all those 6 properties. Now, come to the example of subspaces. So, if V be a vector space over the field R, then S equals to 0 means S is the subset of V containing only 0 vector, and S equals to V, the whole set V are subspaces of V. These subspaces are called trivial subspaces of V. Set of all 3 by 3 skew symmetric or symmetric matrices is a subspace of a vector space V defined as V equals to M3 by 3. So, like all 3 by 3 matrices having real entries forms a vector space. If you take subset of the set of all 3 by 3 matrices, let us say a subset containing all the symmetric matrices, then this set will form a subspace of the earlier vector space. Similarly, the set S x1, x2, x3 belongs to R3, where x1 minus x2 plus x3 equals to 0 is a subspace of R3. Let us try to show it. So, we are saying that the set S, which is having element x1, x2, x3 such that x1 plus x2 minus x3 equals to 0. So, these belongs to R3 is a subspace of R3. So, how to show it? So, we will say first the 0 vector of R3 is given by 0 0 0, the origin of 3 dimensional coordinate space. Now, here x1 is 0, x2 is 0, x3 is 0. So, if I take 0 plus 0 minus 0, it will be 0 only, which is a vector in S also. This implies S is non-empty. Now, let A, B are two scalars belongs to R and x1, x2, x3, y1, y2, y3 are two vectors in S. Then what we are having? Since x1, x2, x3 is a vector in S, so x1 plus x2 minus x3 is 0 and y1, y2, y3 is also a vector in S. So, y1 plus y2 minus y3 equals to 0. Now, A times x1, x2, x3 plus B times y1, y2, y3. So, what we are having here? We have to show that it is also a vector of S. So, it will become ax1, ax2, ax3 plus by1, by2, by3. It is ax1 plus by1, ax2 plus by2, x3 plus by3. So, to be this vector in S, this component plus this component minus this component must be 0. So, let us see. So, we are saying a x1 plus x2 plus b y1 plus y2 minus the third component. So, I have written this particular thing as the sum of these two vectors. This equals to A times x 1 plus x 2 minus x 3 plus, because x 1 plus x 2 from here and x 3 is coming from here, b times y 1 plus y 2 minus y 3. This equals to a times 0 plus b times 0, because x 1 x 2 x 3 is a vector of S. So, x 1 plus x 2 minus x 3 is 0. Similarly, y 1 y 2 y 3 is a vector of S. So, y 1 plus y 2 minus y 3 is 0, and this equals to 0. It implies this addition is also belongs to S. So, if I take any two arbitrary vector of S and the two scalars A and B, A times first vector plus B times second vector is also an element of S. So, from the previous result we are saying that the set S is non-empty because 0 vector is there, and then it is satisfying for any two vectors u and v and the two scalars A and B. AU times BV is also an element of S. So, hence S is a subspace of R3. In the same way, the set S x1 x2 x3 belongs to R3, where x1 equals to x2 equals to x3 is also a subspace of R3. So, what kind of vectors we will be having in this subspace? Where all the three components are equal, means the first component, second components, third components, alpha alpha alpha, where alpha is a real number. So, certainly 0 0 0 when you take alpha equals to 0 will be there. So, S is non-empty. Now, if you take two vectors alpha 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 and beta beta beta, then the sum will become alpha plus beta, alpha plus beta, alpha plus beta. So, the three components are equal. So, then the sum is also a vector in S. Similarly, if you take any x 1 x 2 x 3 and multiply with alpha, let us say A. So, ax 1 ax 1 ax 1. So, it will be all three components will be equal. So, all the properties hold for this particular example also. Now, come to the last one, x 1 x 2 x 3 belongs to R 3, x 1 plus x 2 plus x 3 equals to 1 is not a subspace of R 3. So, what I am saying? I am taking a set S x 1 x 2 x 3 belongs to R 3 such that x 1 plus x 2 plus x 3 equals to 1. So, what I am having from here, and so if I take 0 vector, then 0 plus 0 plus 0 is not equals to 1. What it is saying? That the 0 vector of R 3 is not in S, and hence S is not a subspace of R 3. Further, if we have a subspace of R 3, then what are the possibilities? Either it will be origin, or it will be a line passing through origin, or it will be a plane passing through origin. So, here I am telling you the geometrical interpretation of a subspace of R3. So, if you are having a subspace of R3, either it will be origin, that is 0 0 0, because that will be a trivial subspace of R3, or a line passing through origin, or a plane passing through origin, or the space R3 itself. So, first and last are trivial subspaces, while the middle two are non-trivial subspaces. So, only these four possibilities we are having geometrically for subspaces of R3. We are having some of the important results on the subspaces. One of the important result is the intersection of any non-empty collection of subspaces of Rn is a subspace of Rn, or in simple language I can say, if you are having two subspaces of a vector space V, then their intersection will again be a subspace. In case of union, what we can say? In general, the union of two subspaces of a vector space may not be a subspace. When it will be subspace, then one of them is contained in other. So, what I want to say, if you are having let us say a vector space V and you are having two subspaces S1 and S2. So, if you take the intersection, so this is intersection. So, if S1 S2 are subspaces of V, then this intersection will be always a subspace of V. But if we are talking about union, so if you are having a vector space subspace S1 and another vector subspace S2, then their union may not be a subspace, but it will be a subspace certainly when one is contained in other, either this case or if this is S2 and this is S1. So, either S2 is contained in S1 or S1 is contained in S2. How to see the intersection of subspaces? I have given two examples after the definition of subspaces. One was we are having x1, x2, x3 belongs to R3, x1 plus x2 minus x3 equals to 0. So, and we have shown that S1 is a subspace of R3. Another example I have given that time that x1, x2, x3 belongs to R3 such that x1 equals to x2 equals to x3. So, again this S2 is also a subspace of R3. What kind of element we will be having in S2? 1 1 1, 2 2 2, 0 0 0, where all the three components are equal. And what kind of element we will be having in S1? Where the sum of first two components equals to third component. For example, 1 1 2, 3 4 7, like this. So, 3 plus 4 equals to the third component 7, 0 0 0. What is the intersection of S1 and S2? So, here intersection will be only the 0 vector, because this vector is satisfying both of these properties. no other vector in R3 will satisfy this particular property, because this property is saying that all the 3 components are equal, and this is saying the sum of first 2 component equals to the third one. So, what we are saying from the first one, x 1 plus x 2 equals to x 3, and from the second one, x 1 equals to x 2 equals to x 3. So, if I write x 1 plus x 2, so from the second one x 3 equals to x 2, so equals to x 2. So, from here what I will get, x 1 equals to 0, and if x 1 is 0, so x 2 and x 3. So, only this vector will be in their intersection, and it is a trivial subspace of R 3. Now, we are coming another important definition, that is linear span. So, let V be a vector space, let S V 1 V 2 V n be a non-empty subset of V. So, S is a set of vectors where vectors are coming from V. Then the set L S defined by C 1 V 1 plus C 2 V 2 up to C n V n, that is the linear combination of vectors V 1 V 2 V n, where all these coefficients C 1 C 2 C n are coming from real set of real numbers, is a linear span of the set S. So, for example, if I take S equals to 1 0 and 0 1. So, S is a subset of R 2. We are having 2 vectors from R 2. Now, L S will be C 1 1 0 plus C 2 0 1, where C 1 C 2 belongs to R. So, what this will become, C 1 C 2. So, what is L S? L S is C 1 C 2, where C 1 C 2 belongs to R. And what is this? This is nothing, just the space R 2. So, here linear span of 1 0 and 0 1 is R 2. Similarly, if I take 3 vectors 1 0 0, 0 1 0, 0 0 1, then linear span of S will become like the earlier one, C 1 C 2 C 3, such that C 1 C 2 C 3 belongs to R. And what is this? This is R 3. If I take any arbitrary example, in R 3, let us say I am having a set 1 2 0 1 1 minus 1. Then linear span of S is C 1 times 1 2 0 plus C 2 times 1 1 minus 1. So, what is this? I am having C 1 plus C 2, 2 C 1 plus C 2 minus C 2. Okay. So, this is the linear span of this set. Another example I can take this one. S equals to 1 1 1 and 2 1 3. So, what will be linear span of S? So, again I will take C 1 1 1 1 plus C2 2 1 3 and C1 C2 belongs to R. So, this will be C1 plus 2 C2 C1 plus C2 and C1 plus 3 C2 and C1 C2 belongs to R. So, what is this? How I can represent this set? I can represent this set as x1, x2, x3 such that twice of x1 minus x3 equals to x2, because if you take 2 times of this, so 2 times of this will become 2 C1 plus 4 C2 minus x3. So, minus C1 minus 3 C2, it will comes out to be C1 plus C2 and which is x2 only. So, this is the linear span of S, and we will see that it will be a, you can easily prove that it will be a subspace of R3. So, we are coming to these results only, that let Vf is a vector space and let S be a non-empty subset of V, then the linear span of S is a subspace of vector space V. Moreover, this subspace is the smallest subspace containing S. What I want to say? If V is a vector space, S is a subspace of V, then the linear span of S is the smallest subspace containing the subspace S. So, I am leaving the proof of these two results as an exercise. Now, we are going to define some of the important subspaces. So, if we are having a m by n matrix given by the entries a11, a12, a1n, a21, a22, a2n like that, where a I j are real numbers. So, all these entries are coming from the set of real numbers. Then the row space of A is given by the linear span of the rows, where each row is a vector. Similarly, the column space of A is given by the columns of the matrix A, linear span of the column of the matrix of A. Then we are having null space of A. So, null space of A is x belongs to Rn such that Ax equals to 0. So, all n dimensional vectors from Rn, if you multiply those vector with A like A into x, you get the 0 vector. So, all those the space of all those vectors x from Rn is called null space of A, and it is a subspace of Rn. The set, sorry, it should be R here, R A, not null space A. So, the set R A is all those m dimensional vector B such that Ax equals to B for some x belongs to Rn, and it is called range space of A. In general, column space of A equals to range space of A. So, we are saying these are the 4 important subspaces related to a matrix, and we frequently used these subspaces in machine learning, especially for dimensional reduction concepts like principal component analysis and all kernel based dimensional reduction algorithms. So, one should know all these 4 subspaces. So, in this lecture we have learned about vector subspaces. We start with the definition, then we have given an alternate definition, then we have given some of the example of subspaces. We have seen For important subspaces related to a matrix, we have seen some of the important result like the union of subspaces, intersection of subspaces, and then linear span of a subset of a vector space, which is again a subspace. These are the references. I hope you have enjoyed this lecture. Thank you very much.